Hey, thank you everyone for coming to my talk. I'm happy to announce, I think, like last time I checked, we're bigger than the main stage, so success. My name is Ignat, I work for Cloudflare, and today we're going to talk about Linux kernel keystore. Some show of hands, who here doesn't know Cloudflare? Yes. Like, I said, like if someone raised hands, like there are always like 1, 2 hands, but no hands. Like everyone knows we break the internet once in a while.
Hire interns, right?
We just started. That was because we broke the internet. We wanted more like younger people to help us fix the internet, please.
Or you're out of people who want to break it.
Yeah, by the way, that's a good point. We're actually doubling down our internship program. So if you're interested in doing internship at Cloudflare and teach us how not to break the internet, please apply. And you can even talk to me directly. I will guide you and talk about the different teams and opportunities that we have. You can go into a Rust team and teach them not to use .unwrap or something. I don't know. Okay, how many of you know that Linux kernel actually has a key store? Oh, a couple of hands. Good. Go. Yeah, a little bit about myself. I do Linux at Cloudflare. I'm passionate about system security and performance, and I enjoy low-level programming. So Linux kernel, device drivers, bootloaders, and other stuff written in C and other unsafe programming languages. So I don't write Rust. It wasn't me who wrote the unwrap. So. On a related note, I'm a fugitive programmer, according to US NSA, because they kind of banned C and C++. And the reason they banned is like that NSA, since some time ago, issued a recommendation that organizations use memory-safe languages when possible, because like they kind of like in big companies, most of the security bugs due to unsafe memory usage. Which actually didn't help Rust, right? So I like Rust ecosystem, so I will keep making jokes about it. But this is like the whole point of our talk is about memory management and how can you avoid these typical bugs and like what can an operating system actually do to help you. And before we get to the key store, let's talk about like basic operating system design. So Linux, like many other operating systems, even inferior ones like Windows and macOS, has a concept of address space isolation. So what does that mean? Like modern operating system are multitasking, so obviously you have like many programs running at the same time on your machine, and each program has an assigned basic region of memory, right? So what is like from a high-level perspective of processes? So it's like your main logic, the logic you program, right? So it's also like the libraries that you use. So you don't program all the logic yourself. You're obviously utilizing some libraries. There is a data section where like your temporal global variables are stored. And there is like either one stack or multiple stack if you have a multi-threaded application for your stack variables, right? And the same actually happens inside the kernel space, although like the Linux kernel and many other operating systems, they're not like separated, so everything runs in the same address space. So you have the main kernel code, you also have static and dynamic data, like constants and variables. You also have drivers, and like this is one of the key differences between normal processes and the kernel. If you take a driver, it has literally access to everything. So like don't take drivers from third-party sources. And also you have like kernel stacks. And the whole point of the memory address space and memory address space isolation that anything here can access anything within your process, right? And inside, it's the same thing inside the kernel. Like anything in the kernel can access anything else. So this is why if you load a malicious driver for some device, it actually can access everything else on your system. So you have to be very careful. But the whole point of our isolation that you cannot access directly the memory of other processes. Like the operating system will not allow you to do it. And also you cannot access the memory of the kernel itself. The operating system ensures that you can't do it, right? Now let's actually like zoom in into one process, and like we have all these 4 boxes, and like actually zoom into the data section. So what's kind of, again, from a high level point of view, what you can have in your data section. So it's like some kind of like program internal state, right? Your global variables go there. You can have temporarily like user or customer data. If you programming a web server, like it receives some requests from users, so it's temporarily in this RAM, right? And most importantly, what you can have your cryptographic keys. Again, the typical example is like if you have a Nginx, your web server, it handles HTTPS traffic, so the private key for your certificate lives somewhere here, right? And the whole point of address space is that if for whatever reason either your main logic or your library becomes malicious, either you have a code vulnerability or you kind of take a vulnerable library which has been exploited, your data is also becomes vulnerable because all that code can freely access anywhere else, right? But as we just seen, not all process data is created equal. So like what if your application internal state is compromised, someone leaks it? So well, it depends, like it can be good or bad. Like somebody sees your internal variables, there is some crap there, so it depends. But it can lead to further compromise. So if your internal variable, for example, can control your application flow, that's a bigger problem, right? Well, if user or customer data is being compromised, you have a privacy leak. Like who here knows what happened to Equifax many years ago? Yeah, so the Equifax breach, it's much, much worse. There was a big lawsuit, they have to pay a lot of money, but they're still around, right? So it's kind of like not end of the world. What is end of the world if you have a cryptographic key compromise? So it's full data integrity, full security compromise, and total integrity takeover. So it's, who here remembers Heartbleed a long time ago? Yeah, a lot of keys were leaked, and kind of like the whole point of internet trust is based on the fact that you can prove, the server can prove its identity, but someone, like now it becomes obsolete, right? Like anyone on the internet can pretend they're google.com or everything, so everything is busted. So yeah, you cannot reasonably protect everything in your application from vulnerabilities, but can you do something better to protect yourself from the most important things, which are cryptographic keys? So what are the typical ways a cryptographic key can leak? And the typical thing is like untrusted inputs and out-of-bounds memory access. So imagine like you're writing your code and like stuff that you need is somewhere in your RAM, right, in your application. And also, as I said, if you're writing a web server, your server private key is also somewhere in the RAM. So normally your application is programmed, or you program it, to only be able to access stuff, right? But if your application has a vulnerability, so an attacker can control the flow of your application, it can direct your application to literally access this with no restrictions because it's the same address space, right? And this is exactly what happened during Heartbleed. So, and malicious TLS extensions, like you can inject uncrafted data, and it will force the server to read past the desired boundary, right, and leak the cryptographic key. Cool? So yeah, out of bounds are a typical security vulnerability. Like arbitrary remote code execution, like there is no description here, like, yeah, if your application is susceptible to this, like attackers can control your code remotely and exfiltrate every data. Like, who here remembers log4shell? The Java thing, right? Yeah, so a buffer use is a typical error. So this is kind of like a self-contained C program that you can then copy-paste from the slide and compile. And you see it has two functions, like encrypt and log completion. So like it's a very toy and specially crafted example, but kind of it illustrates the point that first you wanted to encrypt some data and then put a log line like, I'm done, good, right? But here you make a mistake, right? So like, here you forgot to initialize the variable, So yeah, you have your encryption key, hunter2, and just the message you wanted to output, you forgot to initialize. And you kind of like, if you compile this program without any compiler security tricks, you will see that you just logged your encryption key easily. This is kind of a special crafted example, so everything is aligned to make it perfect, but it does happen in the real world, right? So what happens here basically is you have your process or thread stack. This is where your main function executes. Now you call the encrypt or decrypt function, so you kind of allocate a little bit of stack. You put the key, encryption key somewhere on the stack, for example, and if you don't clean it up after your function exits, so it stays there. So the next function you call, it kind of takes over the same space and then can accidentally kind of leave the key. So this example is like leaking from the stack, but the same thing applies if you allocate memory via a heap. So this is why if you ever deal with some kind of security requirements and cryptographic keys, like all the standards shout that you need to zero the memory where the key was stored after you're done using it. But these requirements are kind of rather old. It's easy to do it in C and C++. It's much harder to do it in Go or Java with their it's almost impossible to do Go and Java because of the way how they manage memory, right? Debugging info and tools can also leak your cryptographic data. So what if your application crashes? So anyone here worked with core dumps? Yeah. So yeah, for debugging, a core dump is basically a memory snapshot of your application at the time of crash, which operating system conveniently provides you to debug your bug. But it's a full memory state, so it can have cryptographic keys, and if you store it somewhere and someone else has access to it, they can really exfiltrate things. So how do we solve this? Well, we can try to fix all the bugs, right? If it was that easy, we'll probably not have this conference in the first place. So again, but what we can do is like, yeah, we cannot protect from everything, but what we can do specifically for the most important part, for cryptographic keys. And what if we piggyback on the idea of address space isolation, right? What if we use the operating system concept? So what if we, instead of having only one process, we create another process, right? It will have its own data section, and we move the key there, right? And then we will have a very streamed down, very simple, easy to reason about logic, which just helps these two processes to communicate, allowing this main process to use a cryptographic key from another process. If you ever used SSH, are you familiar with SSH agent? Right? So this is exactly the same model. And apart from the usability improvements that you don't have to type your password for your key every time, if you store your key in an agent, you're kind of using this. So like, the idea here is this is a very complicated code that is likely to have bugs, like network facing, and it's your web server that can be attacked, right? But even somebody finds the vulnerability, they start controlling the application, they can never get to your key because it's in a different address space, and the operating systems ensure that you can never access the key. But you can kind of use the well-defined interface to use the key, right? So I call it like a key agent model, so you have two processes, like main and a helper. Yeah, the main process does not have access to the cryptographic material directly, and they communicate through a well-defined interface. And the agent process is usually never processes untrusted input, never network facing, it's a local process running on the system. And yeah, think of it as an agent as like a software security key if you use like YubiKeys or hardware keys. There are drawbacks to this, is like now you have this problem, now you, instead of one application, need to develop two, right? You need to design this well-defined interface, it has to be like really locked down enough, but enough for you to do what you want. And you need to somehow design the communication protocol between the two processes. You're using like Unix domain sockets, shared memory, whatever, right? Or communicate via files, that's also possible. And ideally, your agent has to somehow authenticate the main process. So even like this lacks with SSH agent, basically anything on your system can talk to SSH agent and use your key. So you have to be very careful. So this brings us to the Linux kernel key retention service, or AKA Linux keystore, just for short. So what if we take this model, right, and replace the process 2 with the Linux kernel, right? It's another address space, as we learned, like why not? And we already have the well-defined interface called system calls. How do you call into the kernel for various features? So in a nutshell, this is exactly what the kernel key store does. It stores cryptographic keys as kernel objects. And it was initially designed to share keys with the kernel services itself, like the kernel, for example, if you use full disk encryption, the kernel needs a key to decrypt your disk on the fly, and you need to somehow provide it to you. So you would use this service, but it was later extended to be used by other programs. So like you can treat keys as kernel objects with different file permissions, and the same as you have on regular files on the keys. So you can have a very granular access control to your keys depending on the application. And surprisingly, for a kernel feature, it's very well documented, so easy to start. So yeah, so how does it look internally? So there are two types of objects in the Linux kernel key store. It's like there are keyrings, which can contain links to other keyrings, and keyrings is like a collection of keys, and there are actually key objects, the objects that store and protect the actual cryptographic data, right? So, and it's very similar to a file system structure. So keyrings are like directories, keys are like files. The only difference is a key can be simultaneously in multiple keyrings, right? And keyrings are kind of the enforcement of the lifetime of the key. So key cannot be like dangling by their own, they always have to be attached by a keyring. Yeah, so keys contain actual cryptographic material. You can read and write the keys if you have appropriate permission. They do cryptographic transformation. There are several key types, which I'm going to go into the detail, and they're similar to a file. And keyrings, they're like a collection to keys, and they enforce the lifetime of the key. They can be explicitly created, or there are special keyring types called thread, process, user, and session. I will also describe these in more detail. And yeah, they're very similar to directory. So a lot of text, so like, let's go to an example. And as I usually like to say, everything here was copy-pasted from a real terminal, from my dev machine, so consider it as a demo. But it never fails because I already did it, right? So yeah, this is my bare bones Debian Linux, and what I can do is like I can create a new keyring and attach it to my default user keyring. So I do, like everything in Linux, there is a system call which provides the functionality, and there's obviously a command line wrapper tool which we'll be using in this demo to show the functionality. So I'm telling my system to create a new keyring, call it my ring, and attach it to my default user keyring, right? And every key or keyring object in the kernel is designated by a unique integer. We'll call it a serial number, so you can track the difference between the object via this. So now I have my ring, right? And now I can create my key. So I'm adding a new key called my key, and my secret that I want to store in the kernel is hunter2. So I'm adding this to my keyring. I have another serial number, and then I can show what my user has access to, right? So I have my session keyring, my user keyring, my custom keyring, and my key. Okay? Yeah, so we can see by serial numbers, I created this key and I see it here, and this is my keyring, right? Everything is here. And then because I have access to that key, I can read it back. I can get the secret stored in this key just fine. Now a more complicated example. So imagine you have two users on the system, Alice and Bob, and they want to share a secret. And they are like regular users. As you can see, they are not part of a common group or anything. They're totally newly created, separate users on your system. So imagine Alice wants to share a secret with Bob. So what Alice can do, she can add her hunter2 secret to her user keyring, for example, right? What Bob can do, Bob can create a new keyring, a collection of keys, call it from others. And what Bob can also do, Bob can change the default permissions on his keyring to allow everyone on the system to write to it. And writing to the keyring is kind of safe. You allow other users to put keys into your keyring, but never get them back. So now if Bob communicates his new keyring serial number to Alice, what Alice can do, she can move her secret to Bob's keyring easily. And now we can see that Alice doesn't possess the key anymore that she created, and Bob actually has access to the key, and Bob can read the secret. So Alice just shared the key with Bob on the same system, and Bob has the key in his possession. So now let's go to special keyring types. So for now we were using custom keyrings, but there are some special keyrings automatically created operating system for your convenience, and they have interesting properties. So there are process keyrings, which can be session keyring, namely process keyring and thread keyring. So the most interesting ones are the two ones here, process and thread. So process keyring is an automatic keyring that your process already has, and it's private to your process. No other process can actually read or write to that keyring. And when your process dies, that process keyring is destroyed, and all the keys that are in that process keyring is also automatically destroyed. And the same thing for a thread, but for a particular thread. So imagine if you're, again, writing a web server which handles multiple domains with multiple private keys for different certificates, right? So and each domain can have their own dedicated thread, and even within the same web server, the threads cannot access each other keys very easily if you use the thread keyring. There is a user keyring, and the session keyring is basically available to your current process and all children of your current process. I will show an example later. And you have also the user keyrings, which are shared between all processes with the same user ID. And user session keyring are system level. They're very similar, but not important from this presentation. There also have a special type called persistent keyrings. Persistent keyrings the name is misleading, so they never persist your data on disk or something, but they're keyrings that are specifically designed for cron jobs, because all these the life cycle of these keyrings are tied to a particular entity on your operating system, either a user ID or a process. So they are created and destroyed as the respective entity is created and destroyed. Sometimes you have a thing like a cron job, which runs once an hour, right? And it needs access to a secret to back up your database, for example. So you cannot easily use a process keyring here because it will be recreated every time, but you can use a persistent keyring, which will not be destroyed for each run of your cron job. Let's see the session keyring example and why it's very powerful. Let's say, so again, I'm adding my secret, but imagine I'm SSHing to my machine. So I'm SSHing here remotely. This is my shell. I'm adding my secret to my session keyring, right? So I can see that, the keys that I added, I have possession for it. Now, in another terminal, what I can do is, and again, you can copy paste and try it yourself. Anyone familiar here with Linux eBPF? The hooking system you can use to trace Linux internals. So I actually can create a debugging probe, a BPF probe, on a function in the Linux kernel, which is responsible for securely destroying a key, right? So I'm running it here. And as soon as in the first terminal, I just log out of my SSH, I will see that my key was automatically destroyed. Why it happens? Because I added it to the session keyring, right? And when I exited my SSH session, my session keyring was destroyed. And all the keys contained in my session keyring were automatically destroyed by the operating system. So I'm not risking leaking out my keys even if my connection is dropping. An operating system will ensure that it happens, right? And When I SSH again, I no longer have the key, and I can even see the session keyring serial number is different because the operating system recreated. Why it's important? It's actually for the same use case I mentioned at the beginning. You have to securely destroy your keys where you're not in using. If, for example, even if your application is written in Java and it suddenly even crashes, so it doesn't even have the ability to execute any cleanup code, if you use the kernel keyring, the operating system will still automatically clean up all your keys without you having to do anything else. So one of the useful features of this is like if you select the appropriate keyring type, you can ensure that your keys will be securely destroyed when you're not needed. So you're tying your life cycle of your keys to your code. Yeah, and even the application is crashes, and it will never be seen in the core dump at all. Okay, clear so far? So we've been discussing different key types. What are the key types? So far we've been using the most simple key type called user key, and the idea here is the following. So imagine you have a process which has some secret, right? So that process can ask the kernel, the Linux, through a respective system call to create a kernel key from it, right? And then another process, if it has appropriate permissions, can read that secret back. There is a variation of this key called logon key. So again, it starts that the process has some secret. It puts it inside the kernel, but the operating system here guarantees that that key can never be read back to another process or even to the same process. It's basically the primary use case for full disk encryption. So when you start your system, you provide your password, right, to unlock your disk. It's stored in the kernel. The kernel can decrypt your disk on the fly, but there is no way any other processor, malicious or not, or virus can read that key back from the kernel because the operating system enforces it. So if you use a reasonable Linux operating system, reasonably recent operating system distribution, and you use disk encryption, which you should, you will notice that your disk encryption keys are actually stored as logon keys here. There is another key type that I really like. It's called asymmetric key. So imagine you don't have a secret, but a proper RSA key, right? So you can store it in the kernel. And another process, if it has the appropriate permission, it doesn't have to read it, but it can use it via a handle. So it can ask the kernel to sign or decrypt data with that key without having access to the cryptographic material. So here is an example how it's used. So we can generate a new private key with OpenSSL. We needed to convert it to PKCS8 format. This is what kernel understands. And then we can add it as an asymmetric key to the kernel, and then we can actually ask the kernel to sign something with that key, and then use OpenSSL to verify it. So this is kind of like the basic building block to replace the SSH agent that I mentioned in the beginning. Actually, everything that I'm presenting today and more, we have in a public Cloudflare blog post, and that blog post contains an experimental proof of concept patch for OpenSSH. It kind of adds that functionality. So instead of running SSH agent on your system, if you patch OpenSSH, you can just store your private keys in the kernel and use them to securely connect to the servers. Cool? So how can you use this functionality as a very useful key management building block and to build secure architectures? Right? And to achieve that, the main question is, how can we actually provision these application keys without the cryptographic material ever being exposed to user space applications? Right? So the problem we are trying to solve is, remember the Heartbleed and all the problems that we encountered, right? Like, if you have a bug in your code and your cryptographic material is ever been there at least once, there is a risk that your bug could be exploited to exfiltrate it. So the whole idea here is like, how do we ensure that plain text, that secret, never hits your application code at all? right? And there are two more key types which can help you with that. So one is encrypted key. So imagine your kernel already has some kind of key inside called a wrapping key. An encrypted key is basically your secret, but it's wrapped by another key. So even if it's your application, it's encrypted. So your application doesn't have access to its to the real plain text material. And once you insert it in the kernel will automatically use the wrapping key to decrypt that key, and then you can use it. But if you try to read it back, the kernel will encrypt it again. So like in user space, that key never exists in plain text functionality. But this kind of like creates a chicken and egg problem, right? So, but how do you provision that wrapping key, right? So, and for that, there is another key type which helps. So instead of just a wrapping key, we replace it with the TPM. Who here is familiar with the TPM? Yeah, cool, many people. So Trusted Platform Module is a small cryptographic chip present in all modern laptops and servers now. So you can really be sure you have it. So instead of the TPM, and again, you have this wrapped key, but it's not wrapped to a software key, it's wrapped to your TPM, right? So when you insert it into the kernel will use the TPM to decrypt it. But when you read it back, it will encrypt it again. So in this scenario, you can build an architecture that the plain text cryptographic material never hits your application code in plain text. TPMs are kind of like cheap and slow powered devices, so it doesn't make much sense to kind of like ping them for every key. It will be very slow. So a useful approach is actually having a combined schema. So you have like a process one, you have some kind of special provisioner process, and if you're doing like some cloud, or you can have like cloud KMS or HSM, I don't know, anyone uses like AWS key services or something like that. So something like that, right? So like anything that your cloud provides. So what that cloud can do, for example, it can provide a wrapped root key to your machine's TPM, right? And as a trusted key, so the provisioner can insert it into the kernel, and the kernel will use the TPM to unwrap it once. And then for all your other application keys and secrets, this could be the trusted key, and these will be encrypted keys, right? So for other keys, you will use that root key to decrypt all other keys. So in this schema, you have roughly the same security as before, but you only like hit the TPM once per boot, for example, and for every other keys, you just use a quick software operation. Yeah, so applications can never see the plain text cryptographic material in their process address space. The problem with this approach is that you have to build that architecture, right? You have to somehow make your application still aware of your cloud HSM or KMS, right? You have to, the inconvenience here is you have to encode their SDK into your code, right? You need to know how to reach that centralized KMS HSM system. You need to know the URI endpoints, blah, blah, blah. And there is kind of little administrative control from a DevOps or SRE perspective, which applications are grabbing which keys. Yeah, and ideally your HSM system needs to somehow authenticate requested application. Even though it's just giving up the encrypted blobs, you don't want to like handing out these encrypted blobs to the whole internet, right? So some hackers can crack it or whatever. And this is where Linux can help, and again, a little bit. So there are actually two system calls in Linux that allow you to insert keys in the kernel. So far we're been using the add key system call. And the semantic of add key system call is if I'm an application, I have, hey kernel, here's my secret, like create a key object from it. But I'm responsible for giving the blob to the kernel, right? So like in case of user keys, it will be a plain text blob. In case of trusted and encrypted keys, it will be the encrypted blob, but I'm responsible for someone getting it from somewhere and giving it to the kernel. But there is another system call which we can use. It's called request key. So instead of, like, I'm now can be a very dumb application. I'm not giving kernel anything. The semantic of the system call is like, hey, kernel, give me my key. And I don't care where you take it from, right? So it kind of like gives you this centralized operating system API to get your keys. But how does it work in kernel? Obviously, everyone's setup is different, and the kernel by default doesn't know where to get the keys from, but you can help it, right? So it uses the following setup. So your process issues, and the way how you request keys by free-form string ID. So the kernel, your application says, give me my key, and my key ID is cloud :app :key1. So what the kernel does, it creates like an internal placeholder where the key will be located. But obviously, the kernel by itself doesn't know where to get your key material from. So it calls out to a specialized user space helper process, which your administrator or you as an owner as a system can configure. And technically, you can even, that process by default for most distributions is written in C, but you can kind of configure it to write modules for it to actually add your business logic where to get the key material from. And you can actually have several modules depending on the path. So for example, if the key ID starts with cloud, you can write a module for cloud, and that module will call out to your cloud HSM and actually get the key material. If the key is already there, so the HSM will return the key material to the process. It will notify the kernel that the key material is available and send it to it, and the kernel will then notify your application that the key is ready. So the difference in this schema, so this could be managed centrally by administrators or people, SREs, who people set up your system, and you as an application developer doesn't have to care at all. Is your system using a cloud HSM? Is it like on-prem HSM? Is it like locally generated? Doesn't matter. And even admins can change it on the fly without ever you noticing. Yeah, so it's basically a single centralized operating system API to request key for applications. There is no like KMS, HSM, connection strings, URIs, SDKs, nothing. All you need to talk is the kernel, and your code is fully decoupled from the key storage solution. And it's kind of a more secure way to instantiate keys. Kernel also enforced like some particular process, security properties on that process, so it's much harder to hack. And yeah, and like your administrators have full control of how your keys are instantiated and where do they come from. So basically with request key, if you configure it properly, key management and distribution becomes like a core service of the operating system, as it should be, and not a responsibility of every application developer. I actually wrote a small proof of concept just to illustrate my point, which I wanted to show. And what it does is, it's a proof of concept, so I didn't use a real programming language. It's written in Python, but you can download and try it. And what it does is it's a plugin for the request key system, which allows various applications to generate machine-specific and application-specific keys from your local TPM. So I'll just show you how it works. You don't have to really care about the string. This is how you would configure your request key for your custom module. So if you download my module to try it, you can just copy-paste this. And it will work. So in this example, I'm using, and my toy application will be, again, the keyctl application. So what I'm telling the application, I'm asking the kernel, hey, kernel, give me my key, which is starts with TPM2 derived test, because the key will be generated from a TPM. 32 means I want a key with 32 bytes. And I want my file system path as my unique identifier for the key, right? And the kernel will generate the key. We can print it. Obviously, if you retry it, you will get different bytes, but because you have a different TPM. But here is the useful part. So I can now delete that key, right? And I can re-request it again with the same parameter. So now it will be a different key. You see the serial number is different. But if I print it, the bytes are the same. So my module, what it can do, you can have a machine application specific key without actually the need to back it up. So it's very useful for diskless and ephemeral systems. For example, if you have a small network router with read-only file system, you can use this approach to have a consistent SSH key, even though you don't have any storage, because the TPM allows you to recreate the key on the fly when you need it, and it will be the same key cryptographically bound to the same machine and to the same process. So for example, I can actually, again, I'm removing my generated key, and what I do is I move my application to a different file system path, right? And I rerun the same command, but now the key is different because I'm requesting the kernel to create a unique key for a specific file system path. So every application on my system at different paths will have their own unique separated key, okay? And it also takes into account the calling user ID. So if I run the same command, but like as root, I will also get a different key. So different users, different applications for different file system paths have different unique machine-specific keys, which kind of brings my system closer to what mobile devices are doing today. There is another interesting mode which I find useful is instead of the path unique parameter, I can request a checksum, and it will actually cryptographically bind the generated key to my application code. So in this case, I'm regenerating the key, I get some bytes. Now I can move the path again, right? But now I can, even on a different path, I can get the same key because the generated key is cryptographically tied to the code, the application code that requested it, right? And I can prove that it works, so I know if you basically scan the compiled executable keyctl, there is an error message as a string called bad message. I can actually patch it and turn it into bad massage. I'm changing 1 byte here, right? It will still work. I can rerun it again, but now I'm getting a completely different key because my code changed. So every executable has a unique key based on the executable itself, which is, I find is really cool. And there are more tricks you can actually do if you write your own logic. So I guess this is all that I wanted to present today. Hope it wasn't too much. Most of the links are for kernel documentation and man pages for the functionality. And everything that I'm presenting today and more, and the patch to OpenSSH server is in the cloud for a blog in the end. Thank you very much. And if you have any time for questions.